Hmm. Hmm. We got again. We got bidirectional dependency situation because we want to get this 10 off this 13. So we could put the 12 on the 13. Um, why did I want that? I forget now. Oh, so we could put this jack on the queen, right? But we can only do that if this is over there. And the reason we want to put the jack on the queen is the 8 on the 9. So we could put the 9 and get the 2, right? So that is not so easy. So I'm kind of tempted to just throw all this over there. See, 12 goes on 11 or 13, though, and they're all. This is one of those early choices that could screw you for the whole game, right? We want to get this jack free. Why? Because this 9 to get this 8 off the 2 and all this stuff. But, like, and 3 gold is a good card that you want to get. Doesn't matter yet till we get 2. But the point is, if we bury 13 and 11, this card's never going anywhere, and this whole column is dead, right? And that's got 21 in it. Now, 9 is in here, importantly. And if we get that, we could go 8, 9, 10 and stack all this up here, right? But it's under a bunch of scary cards. Like, we need to make some headway first. I mean, okay, we could just throw 8 in the hole, 9 on the 8 here, and these can get ready to go on the 10, right? Because this 4 goes over here, 3, 4, 5. Okay, this is looking good. 8 in the hole, 9 on the 10. 2 pops off. We go king, queen, jack, 10, 9, 8 down here. Well, that doesn't give us that 4 we wanted. Um, but it frees the 13 and all that, right? If we free the 13, 12 on the 13. Um, see, this is funny too, because we could put the 12 on the 13 and we could put the 13 on the 14, but the king is on the queen. Oh, that's a wait, that's a swapperoonie. That just works out. Okay, hold on. Hold on. We're just going to do this. Boom, boom, bam. 10, 9, 8. All right. We're not going to close this gate yet. There's also 7 here, by the way. Yeah. Oh, if we put it to the left and we put the 4 on the 3, 4, 5, the 8, 9 goes here and then we put it on the 7. Let's just do that. Let's just do that. Wait. Let's do this. Okay. Okay. Oh, or we just take 0, right? And get red 6. This is tempting. But we got to get rid of this 8 here. This 8 is bad. Okay, the 8's on the 9, which means we need the 12 on the 13, or the 11, which is below the 13. So we have to basically do that, all right? Which means we have to basically do that and that and that. Do you see what I'm saying? I hope you see what I'm saying. Now we do this. Found you through the creator of Patrick's Parabox. That would be Patrick, creator of the Parabox. Could I explain what's good about this game? Sometimes things are hard to explain. I just like it a lot. I like it a lot. It is the same game over and over. I'll admit that. So if you want variety, this is not really the game for you. You could play the Drifter in that case. See, we kind of want to do king, queen, jack 10, 9, 8. But where do we want to do it? We want to do it in its own column. And the problem is we're going to be, it's going to end in sadness because the 15 would cover the 14, blocking us from moving this 13, 12 there, okay? So this also has to be in its own column. And then even if we clear this 7, which we could, we got no slots. We've got 15, 14, 13, 12. And king, queen, jack, 10, 9, 8. Now, if we could free this 7, we could put the king, queen, jack, 10, 9, 8 on the 7. We could free this 16, which if we could get this 1, all this pops off and this 5 goes here. Yeah. Now the thing about this is we need to clear the king to get this 2 and this 1. So we're in a catch 25 here. All right, a catch 52. Now, how many cards are in the tarot deck? 100 and something? A catch 100 and something. See, I want to attack this, but this 3 is here. But other than that 3, see, you can always, if you're going to clear a slot, you can throw one thing in your empty slot because you get the rest back. But we don't get the rest back because of this frickin' 3. We could put the 6, 7 over here. We could put the 9 there, right? Now, to get the 3, we get the 2, which 7 has nowhere to go. 8 Arcana has nowhere to go. 10 has nowhere to go. 6 has nowhere. So this is very bad to try to attack. This is a difficult moment, guys. This is a difficult moment. Okay, what if I put jack 10, 9, 8 over here in the hole? 15 up, 7 down here. Okay. 13, 12 in this slot. Flop the jack 10, 9, 8 back on the queen or on the king. We could put all that over there. And then 15 just comes down and it's a 1-bagger. So we have 12, 13, 15, red king, which is annoying, 4, 11, 6, right? And the problem with that is we can't do anything with this 4. If we could do something with this 4, we could reflip the 13, 12, lift the king, do something with the floor, put the 13, 12 on the 11, put the king down, right? And then we would have 13, 12, 11. And we could swap that with king, queen, jack, 10, 9, 8 or something, right? And this 6 could go down here. So this is almost something we can work with. The problem is this 4 here. Problem. Good morning. Is every shuffling of the cards made to be solvable? Yes. Yes. Okay. We are gonna do something here. The other sort of thing is like this column, which looks messy, but like this 5 could go in this 6, right? If we pop 0, we put 5 over there. This 18 is annoying. But then this king, this could move on there and free up gold 5, which is useless. Great. Oh, you know what I can do? I didn't even see. I was trying to go for the big clear. We can at least do a small swap Rooney here. All right, we can do this. That doesn't cost us. Now, the problem is, if this were the other way around, we'd be great. If this were king queen, we could put jack 10 9 8 on there. We could put 14 13 12 on the 15. And then we could flip this onto the 6. We would be set. It would be awesome. But that is not what life has given us today. All right. So we need this 7. Which is really annoying. This is a hard board. It's a hard board. What do we do here? See, the problem with red king, if we do this and eat a slot with this, we've got red king, which is kind of a blocker till we get down here, right? But, okay, if we did that, we put this on the 15. 7 is down here, 9, 8, 7. Gold 6 is free. No, it's not, because the problem is once we put this on the 15, we're dead. Because we can't, we have no slot that we could lift, right? So we can't bounce it. We need to bounce this off an empty slot to put it on the 6. Why do we have such a hard board today? Any chance is the new game going to be released by next year? Well, I'm hoping we're getting toward the end. I'll put it that way. I'm hoping that someday we will have a video game that you can play. We are working toward that moment. Why is this so brutally hard? Am I just not seeing something that I should be seeing? We just need a little bit of wiggle somewhere. It's just so scrambled. All right, you know what I'm going to do? I'm going to do the king, queen, jack situation. I mean, I think I just lose. I think I just lose when I do that. Uh, uh. Will the game be out before GTA 6? Good question. I mean, they're currently saying GTA 6 is like next May or something. But you don't know. I mean, they might delay that some more. I refuse to compare. I don't. Let me put it this way. I don't think that gamers who are going to choose what game should they play are going to look at a binary choice. Should I play Grand Theft Auto 6 or world's most challenging puzzle game? I don't think that's how it's going to work. There's too many cards on the board. I agree with that assessment. This is the only thing I see to do, and it really sucks. It really sucks. I mean, we could do some other minor stuff, like put the 2, 3, 4, 5, and then like 5 on the 4 or 3, 4 on the 5. 5 on the 4 gives us 16, 17, which we can't really do anything with at that point. This is really nasty. You know what I wish there was in this game? I wish there was a button that you could hit and it would just like run an auto solver and not tell you the answer, but just tell you if the level is solvable, right? Because if I knew this was solvable, I would think really hard right now, but we might already be dead. Like, I don't. See, we almost could. So we could put 2, 3, 4, 5. We could put 5 on the 4, 3. Red 5 up, and then we want to put like 16, 17 on the 18. That doesn't even help us because we still have a 20, but we can't even do that because the red 5 is up. I feel like I'm just not seeing something really stupid here. That would not be surprising. Someone's going to watch the VOD and go like, you. All right, I'm just going to do this. I don't see anything better than this, and this is probably game over. All right, but I'm doing it anyway. Let's see if we can have that not be game over. Okay. So now we want to put this on a 7. That would be one thing we could do, right? And here's a 7. It's a little bit buried. Okay. Now we have two ways of trying to clear the 7. And both of them kill us, right? So we could do what I said before, which is 12, 13, 14 under the 15 here. And then the 6 is free. And then we would like to bounce this onto the 6, but we can't because we got no free slots. All right. Why did we want to do that? Maybe that doesn't get us the 7. Maybe that just gets us the 0, and like then we could do something with this 6. Whatever. The other one is put the 15 up, put 2, 3, 4, 5 there. Put 5 on the 4. Put 15 on the 16, 17, right? And then you could put 14, 13, 12 on the 15 if you could bounce that off an empty slot, which you cannot. And then you have this over here again where we can't do anything with this 4. Maybe that was why we wanted this, was because we want this 4 to go on the 3. But we can't. Again, like if we do this, we bounce that in this slot. 9, 8, we get 0, which is a very small moral victory. 9, 8, 7 goes on the 6. But we can't lift king up to put the 4 on the 3 because this is still there. New place looks nice. It's kind of a mess. Shouldn't the level generator not do that initially already? Well, sure, but you can get into an unsolvable situation, is what I'm saying, right? That's the challenge of this game, is to not get into an unsolvable situation. Yeah, I don't see, like, the thing is, we already looked at most of the possibilities. The only things that are different now is what we changed with by doing this, right? You think this is lost? I think so too. I think it's been lost for a few moves. Um, let's get our minor moral victory of this. So we're going to do that. All right, so 987 on the 6 or 6 on the 987. And then we lose the game. We got 0. We got 0. Boom. All right. Someone on stream is going to go, wait, you just had to flibble the flob later. And I'm like, oops, I didn't know that. So we have 18, 19, 20 here. 17, 18, 19, 20. Except 6 and 7 are mutually blocking that. So the 17 would have to come later. We could just take that, though. That's an easy clap. We could just take that, though. Hold on. I mean, we could put, since we did just lose, let's like not. If we decide we need this green 5, we could go the other way. But red 2 is easy to acquire. Let's put it that way. Because 0's down here. That's the thing, right? Do we want 0 or do we... 0's a little harder to get. But like 5 can go on the 6. Here's another... So Jack 10 we sort of want. If we clear this 8... No, because that puts the 7 on the 6. This is another twisty board, guys. So what I'm seeing too is the golds, aside from these, are all kind of buried. And that's going to be a problem. So like this 7-6, we can connect it, but where's it going to go? 5-8. That's very rough right there, right? So we got to maybe attack one of these columns. 7 on the 6, 19 on the 18. But then this 3 wants to go on the 2, which is under the 6, which could go on the 7 for now, I guess. So, but by the time we get down to this 10, that's not going anywhere. So we could just start drilling out this column a little bit. And then when we get to the 5, we could put 7, 6 on the 5 and just call that. And then that frees up our 17. So that's pretty good. We could do that at some cost to like covering this king queen. Let's look at this one. 5 wants to go here or here. We've got like a mutual blockage situation for putting, well, again, if we do some of the same stuff here, yeah, I don't know. This jack just has to go on this 10, which means this 6 has to go like over here, which means this 19 has to be free anyway, which means we have to do what we would have done here. So this column is kind of blocked on this column. Let's see if there's any, so we could do this and make some progress, but let's see if there's anything else. 10 on 9, 6, you know, it's the whole same story. So this sort of wants us to do this. So this is a lot of votes in favor of this. 18, same. Let's just do that. Let's do it. All right. What did I say? We're going to do that. 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 And then, so since we can't really do anything with this 10, right, for a while, till we get down here or something, we'll do this. Okay, and that gives us this. Now, we're back to here. We got 9, 10. And we could put this 6 on the 7 if we put the 10 on the 9, but we want Jack 10 to go together, right? Especially, well, if we put 10 on the Jack, 3 goes, and then we can flop them on 9, or 9 on there and get the 21. So we really want both of these to go on this 8. The problem is it gets rid of the 7 that we want to put the 6 on. So we need like 5, and that's under this hole. We just buried that 5, right? Which means we have to deal with this, 7, 6, which means we need these cards that we were looking at before. You see how this game is, guys? Do you see? Oh, say, can you see how this frickin' game is? How so madly we flailed. Okay, let's consider, since this 3 pops, what if we just throw the 6 in the, or the 10 in the middle for now? So we got 10 on the 9, 6 on the 7, 10 in the middle, 3 pops off. 9 is kind of a stickler, but we could lift the 9. 21, 20, 19, 18, 17 all go, which will at least make us feel good. 16. And then the 9 comes back down. So we would have 2 1-baggers. We would, oh, and 10, 9 go together. Oh, that actually works. That actually works, guys. It's a, what am I even talking about? All right, easy game. Easy game. Now, we do this, which we've been wanting to do for a while. Okay. This red 9 could really only kind of go here. This 10 is under a lot of stuff. And this red 8 could, it's got nowhere to go. All right. Let's do the swapperoonie. That's easy. Oh, I was going to double swapperoonie and we can't. Oh, yeah, we can. Could do that. All right. Do we want green queen? Maybe. Or do we want gold 10? Not really. Not really. So I'm going to do this. If we get this 8, all this comes together over there. So we could put 6 over here, 9 in the hole, 9 up, 8, 7, 6 over here, 9 down, 2 pops. Shakur, right? Right? Do you see the gamer moves that we are pulling? Okay. Now what? We still haven't done this. King, red, nothing to do with that. Gold 10, well, we can use that, so. If we wanted to do this king-queen situation, now we could. Or we could try to push these arcanas somewhere. We don't have blue 2 here. We could just get that at a cost of a stupid jack in a slot. You know, I'm kind of seeing this now. So we put 7-6 over here, right? King on the queen, 5 down there. 8, I don't know, in the other slot. 0 goes. 4 goes where we just were, and 7 goes over there. This is kind of wasteful, honestly. Oh no, because it gets rid of all that stuff, so that's fine. And we do that. It's still, it's a little wasteful, but when you pop that many cards, it's maybe fine. Okay. Okay, things are looking up. I have a very positive attitude, as they say in Little China. Um, okay. I mean, this is done. We have won. We have won the day. And I think it's time to do some compiler stuff. Let me get a little bit of a snack. And then we'll go. Did I watch Gabe Newell's interview? No. No, I did not. Back in a second and we'll start compiler. When's the last time I played Last Call BBS? When it came out? But I played the dungeon game. Oh, yeah. Yeah, we do go back and play the dungeon game once in a while. That is a true fact. Am I hitting the gym? No. I'm just doing all my normal things. Okay. Is that too high? A little bit. Doesn't matter. Okay. How's it going, everybody? What monitor setup do I have? I have one monitor. In this context, inline is strange. Yeah, it is, but the thing is, if you insist on putting a hash mark on absolutely everything that's compile time, there's going to be a lot more hash marks. And it's maybe just too much. Okay, let's get started. I wanted to do some compiler stuff this weekend, and sometimes I like to go back to older issues, like longer standing issues that I would like to make progress on, right? And one of those is this general phenomenon where we don't have our own optimizing backend. We have our own backend for x64 specifically. But when we want to optimize a build, we use LLVM for that. LLVM is one of the biggest, most bloated pieces of software ever created by mankind. It's very slow. And for a compiler that wants to have very fast builds, that's really annoying, right? Okay. So in the long term, our goal, of course, is to be able to generate release builds without LLVM there and have them be fast, preferably faster than what LLVM generates. Although that is a multi-dimensional problem because you start thinking about all the machine languages on all the different chips. So that's a big task, right? Big task. But there are some things that get you a little bit more toward that direction. That'll just help in all directions. So one of the philosophies of this compiler that differs from most compilers is, like most modern compilers, and maybe LLVM started this trend, but it sort of definitely was a trend that people talk about in interviews and stuff. And it's motivated by a good idea, because that's how all bad ideas start, is they're motivated by good ideas, right? So the good idea is like, look, you want to keep the complexity of your compiler down to the greatest degree possible, because complexity limits what you're able to do, right? It always does. So if we're going to have these optimizers on the back end anyway, then when we generate initial bytecode from our source code, right? The bytecode is just these pretend assembly instructions. When we do that, we're just not going to be very careful about that. We're just going to be sloppy and generate a bunch of redundant bytecode. Why? because that's naturally what happens when you write simple code generation. And look, if we're going to have these optimizers on the back end that can clean this up anyway, then they'll just do that. And it adds more code complexity and more bugs to try to be more careful about generating the bytecode initially, right? That's sort of the modern compiler vogue. And the problem with that is that optimization is a search problem, right? And then just even emitting more stuff and more data structure, both more bytecode instructions and then more data structures that talk about those bytecode instructions that you use to optimize later and all that takes time and energy, right? And so that's why one of many reasons why modern compilers are so slow. And so one of the several contrarian things about this compiler, and I think this is starting to be a trend because it seemed like the people at the Better Software Conference were totally down with this direction. For example, we actually would like our bytecode to be pretty good just as we output it, right? And then if we do an optimization pass, that's great too. But even just in a straight up debug build, so optimization passes can be inconvenient in a lot of ways. Like you could say, well, just, you know, even for debug builds, just run fewer optimization passes. And in fact, in our debug builds, when we use LLVM, we actually do run a couple of light optimization passes on it because that's actually faster than running the code gen for all the code, right? That tells you how bad it is. So, you could just say, well, just, run a light amount of optimization passes for debug build or whatever. And the thing about that is it also can mess some things up. Like it can make your code more confusing. Because the thing is, code output in the order that it naturally is output when you navigate your syntax tree or whatever data structure you're going to use. Programmers can look at that and understand it. It makes sense to them because it follows the order of their code and stuff. But once you start doing optimizations, you may be turning it into something that's less understandable. And that sort of removes value from the situation, right? So these are all things to consider. But for this reason, we try to emit code that is as efficient as possible, or as efficient as reasonable, without having to run optimization passes. And so what that means is we do little search operations and stuff. So this actually, I feel like I can go back to this example that we did last night. So this is a little 4 instruction byte codes for this function. We were actually testing something, right? So A is 1 over X and B is 1 over Y, and these are the variables. And this dump says that we're printing the bytecode. Very simple function. And never mind that we're not using these values right now. That's something that would be a light optimization pass to like say, hey, you're kind of not doing anything here. But again, for debug build, you don't want to do that because you want to be able to step through this and see the variables. And you might say, well, but if you're not using them, should you be able to step through? And the answer is yes, because this actually happens a lot. Like in a build of a large program, these might be used in some cases, and you might have like some if-defs down below that control whether or not they're used. And it's just annoying to have that stuff. Like when you're debugging, you want the code to do what the code says it's doing. Okay, but the point behind bringing out this example is we're just doing 1 over a couple things, and we only emit the constant for floating point 1. Floating point stands will know that hex pattern immediately. That's 1.0. And we're just doing a couple bin ops, right? And why are we only emitting one floating point constant when we have two? It's because our routine that outputs floating point constants knows that we already did one and it doesn't need to do another one. You feel bloat partly happens over time due to the disconnect between you're making a concrete program and they're making generic cover everyone's use case system. Yeah, that's true for everything. Like game engines like Unity or Unreal are just like super bloated, right? Because they're making something for everybody. And anytime you're making something for everybody, that's just what happens. Visual Studio, canonical example. Register allocation and instruction selection. We're not gonna talk about that right now. We do have systems for that. I wouldn't say that they're the best systems for those things. They just suffice for now, let's say. I think register allocation is an unsolved problem, actually. Because people think they solved the problem and then they just go off and be jackasses for decades. Like the standard answer for register allocation is graph coloring, but graph coloring is not solving the right problem exactly. So what? Right? Okay. I feel like register allocation is not actually that hard. It's just nobody has thought about it the right way. That's my opinion. It's NP complete. Yeah, for sure. But there should be a heuristic that gets you very close to optimal, and then you just tweak some things around to improve it, right? You want to register allocate in linear time for sure. Yes. Okay, anyway. So let's go back to this. So this was a thing, last night we were doing a little compiler stream and we noticed that we were actually emitting more than one floating point constant for stupid reasons, and we cleaned that up. Okay, but now the other thing we noticed last night is when we do a function call, we return a value. And then when we're assigned, let's go to this code actually. This is line 453. You'll see where this came from. That little code we were looking at was an example, but the reason we made that little example is because I just happened to be flipping through the source and I picked a function at random and put a dump on it. And I'm like, oh, we're doing this 1 over twice for it was actually multiple times. The reason it's multiple times is because this came out as a different type from that. So we thought they were different constants, even though they're the same. And then these are all in different basic blocks from each other because they're inside if statements. So you can't be guaranteed that, well, for sure that in not all cases, if you're emitting this one, has this one been emitted, right? So we ended up initting 1.0 4 times in this function. And I was like, what? Why is that happening? All right. But the other thing that's happening here, we call XYZ here. This is just a thing that makes a vector and puts the one in the X, Y, and Z slot of the vector. So here's the call. We're calling XYZ. We're returning the vector as V6. V6 is a pointer to the address of that data structure. It's 3 floats packed together, right? Very simple data structure. Okay. Immediately after that, what do? We take the address of a local variable and copy the result of the function call into the variable. Why do we do that? Because because that's just what happens when you naively output code, right? And so, you'll notice that happens elsewhere too, where we have more function calls down here, line 458. We call conjugate, and 459 we call rotate, right? So if we go down 458, we call conjugate, we take the address of a variable, we mem copy, right? So basically every time, now here we have multiple calls. These are operator overloads, and they're nested calls in here then. And here it's not bad because we're just returning like v23, which points to some newly allocated thing on the stack. Then v23 gets passed. So for chains of calls like that, we're fine. But it's very common to like assign to the result of a call. And when we do that, we're doing double stack allocations and an extra mem copy. And again, that both makes our debug builds slower. Well, and it makes them more confusing because you have more storage. Like if you're stepping through this, you have more storage locations for values than you would like, and that's bad for readability and understandability of the code, right? And then also we're feeding more stuff into the back end for it to like, LLVM is trying to do mem to reg on like a lot more things than it should have to, right? Okay, so all of that is happening. I'm thinking what we should do is make a simple example because so that's for large values, right? Large values are these things that definitely have stack space, but there's also small values, and I think probably the same thing happens for small values. So I just want to go back and make a little simple example. We're going to have return int and return struct, right? And then we'll do something else in a bit. So hold on. Okay. Okay. This is just going to be a vector. It's going to be a 4 vector. All right. So we're going to do that. And then down here, we're going to pre-declare and do an assignment because, a declaration and an assignment are a little bit internally different from each other, and we might have to catch them differently. And then we want return both. All right. Whoops, this is AA. I don't know what I'm doing. Let's put that in that order. All right. So you see, we're just testing these different paths of the compiler. So now we'll build that. So we're we're doing the same thing, but with small values. So instead of take address and mem copy, we're just doing register copies here, right? So we're calling return int. That's going into v2, but we already decided that A is v1. And so we're doing this copy, all right? Now this is interesting though, because last night I was thinking, how am I going to do this? And uh-oh, we lost a peripheral somehow. We got a Windows beep. I don't know what it was. Hopefully it wasn't something we need to stream. Okay. I was like, are we going to need to go do a pre-pass through the tree and like, not really a pre-pass, but pre-visit of the node and like scrape things? And for this case, no, because what you can tell from the bytecode, what you can tell from the bytecode is we're returning v2 and then we're copying it to v1, which means we allocated this value number for a before we did the expression. So in principle, we can just deal with it. That's good. And then for B, here again, you're seeing the Lee and the mem copy. All right. Here, let's make these uninitialized. Just to get some spurious instructions that just emit zero initialization for that, because I really just want to focus on these calls and stuff, right? Okay. So return int, return struct, we looked at those. So then here we're calling return int to v6. So v6 is going to be a. And then here again, we're doing the mem copy. All right. So now here, return both to v9, 10. Again, oh, so in this case, this is what I thought. When it's a comma separated declaration, see this? We're returning to v9 and 10, and then we're copying into v11 and 12, which means we didn't know the locations of those value targets first, which means we might have to do some extra work, or who knows? We're going to have to figure that out. And then in the assignment case, I mean, this is easy because v5 and v8 already existed from way up here. So we're just assigning down there, but again, with waste instructions. So really, if we do a good job, this function should just become call, right? So it's like, well, stack node call, and return, right? So it should be 6 instructions instead of 18 instructions, I think. That would be nice. That would be nice. Here's what we're going to do. We're going to put this to the side just so we remember what the output was. Okay. And then we're also going to do Sokoban. This is with the debug compiler, so it'll take a minute. But we're going to see how many byte. This is the dump of that one function that we had. We're going to see how many bytecode instructions we have in the whole Sokoban game. And by the end of this might take more than one stream. Maybe we'll check our progress in the middle. But by the time we have this down to stack node call, wait, there's 6 calls. 1, 2, 3, 4, 6. So 8 instructions instead of 18. That's still a lot smaller. So by the time we have this down to 8 instructions, we can then see, how does that look compared to that? Your guess is it will go down to 500K. No, I don't think so. I would believe 710K, maybe. I don't know. We're going to have to see. you gotta just realize this is an atypical example, right? Where we're just calling a bunch of functions. Usually you do other things also besides calling functions. Do I think it will make a difference to FPS? Yeah, I think it would. I think it would. In a debug build, right? In a release build, you hope that the optimizer is catching all of these anyway because they're pretty obvious. But also, who knows? Like optimizers are weird. Okay. So I think the first step is maybe we're just going to look at the code and just look and just see how we would do this. And we'll just be kind of slow and deliberate about it. And we might do some cowabunga oriented programming. And then we should be able to have some results in this stream, right? About some of these situations improving. And then maybe we'll get it all, maybe we won't. All right. So in the bytecode builder, we have emit procedure call, all right? If it's a macro, we do this. We're not worried about macros right now. That's a whole different thing. If it's an intrinsic, we just not worry about it also. So we're really looking at down here. I think we have an emit hardened procedure call, right? Yeah. That's really what we want to look at. This thing. Okay. Wait, we have a placement already. And we have a return placements array. This surprises me because I don't see any evidence of this being used. But that's good. It means I was already thinking about this. It may make the job easier. So let's look at return placements. Okay, literally, it's not used at all. Literally, it's not used. Okay. So here we go, num return values. We can't change where return values go yet because they are hard-coded via return register base. Oh. 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 All right, yeah, this is a sidetrack. We might not have progress on this in this stream. It's like the RPG where you're doing the quest and the guy's like, I'll give you this sword to fight the rats with so that you can get the rat trophy. But first you need to go pick bananas in my banana garden. And you don't have a ladder to pick the bananas. And then you need to go get the ladder from the carpenter. Right? So the deal here is during compile time execution, when I initially implemented that, I was like, look, if you're returning 5 values instead of allocating 5 separate things or whatever, we just have this, we store one value, which is the return register base. And then just every return value is that plus the index of the return value. And that's very easy, right? It is very easy till you want to do what we want to do now. And now it's like, no, we need these things to go separate places. This could be a large change, if I'm being honest. Let's see. Oh, God. You don't want to see that many of something that you want to get rid of. Okay. Yeah, see, this is just like the first, there's some number of things that the arguments go in. Um, I thought that was really great and simple at the time. Okay. So, fortunately, this isn't being used in the actual backends as you would expect. Let's look at the places where it's being used. So, foreign function interface, we just use return base. I don't know why. I don't know why we're renaming it slot here. We could fix that. But we just need to know that. And so what we would do is replace this with just like what is the return uh location for return value 0. So basically on this call record, what we're saying is, so what you're saying is on this call record, we just want to have an array of where do the return values go? Right? Which means, of course, we're going to use yet more memory. Okay. Hopefully all of these look like that. So I mean, intrinsics probably only return one value ever. Wait, are we even using that return? Yeah. Oh, we're using 2 for compare and swap. So, you know, basically, here's what we can do again is you always want to do these things in ways that just don't break everything for a long time. So what we can do is we can add this array of return values, and initially it'll be literally exactly the same. It'll be return register base plus 1, return register base plus 2, and so on. And that'll be an array on the call record that we do when we assign return register base, right? And then we'll get rid of return register base and reference that array instead. We'll get everything working. And then we'll check that in and take the W. And then once we just have an array, we are free to change the contents of that array, which we cannot do right now, right? All right. Let's look a little bit more. So that's the intrinsics. And then this is the loop in emit hardened procedure call. And here again, we would just subscript that array. And then in bytecode runner, wait, what? So we already have this other. It's been a long time since I've looked at these data structures. So it looks to me like we already have these. Does call record, I assume call record has a pointer to procedure info. Yes. So really what we're saying is we've already done a lot of this work, which is good. Excuse me. See, here is the loop where we're very explicitly doing these copies. So honestly, I think we just kind of get rid of return base. Like this does kind of just seem like a vestige of the old republic that must be swept away. I did not want to come to Sweden. Well, it wouldn't have been a good time. It was a crazy time for me to try to come there anyway, so it wouldn't have been as good of a talk as it might be sometime in the future. So if you had much more time, you would have wanted to give the rigorous talk with numbers. Yeah, I mean, here's what I, and maybe I said this in whatever clip you saw, but you know, like I saw a Sea of Nodes years ago, and of course, anytime you see a technique like that, you're like, should I, you know, I'm designing a compiler. Should I use this? Should I not? And I was a little bit biased toward no to begin with because it's like, you know, it's like nodes and garbage collection and all this stuff, right? And those are just things that I don't like. However, you have sort of equivalent problems if you don't do that. So for example, we're looking at bytecode. You know, we store our bytecode in arrays. These are basically arrays in buckets of bytecode instructions. And as soon as we want to start moving these around, like, you know, let's say we have a loop and we want to move instructions out of the loop, it's like, well, there's no space to move those instructions into, right? And so you kind of have to solve equivalent problems anyway. And so sometimes ideas that you don't like initially, you would end up doing the equivalent of anyway, right? Okay, but so when I first saw Sea of Nodes, I was just like, does this do something really? Or is it a stylistic difference in terms of how you think about things? And that is kind of a spectrum, right? Like there is such a thing. In fact, it's actually very common of something that's a stylistic difference or that encourages you to do things certain way. And because of that, it means that in reality, your code is going to be kind of different because you know what's encouraged is sort of the way that things are, and if there's a lot of friction in a certain direction, it's much less likely that you'll go in that direction, right? So I guess what I'm trying to formulate here um is it like my question going way back to then was like, is it, does it really make things easy? Or uh not necessarily, right? Like is it just a stylistic difference on things that I would have done anyway? Now that said, I haven't done some of those things. So as we said in the intro to this talk, we do try to emit clean bytecode, but we're looking right now at something that is not clean about the bytecode we emit by default. Um, that said, fortunately, it seems like a relatively trivial problem to fix. Unfortunately, it's one of those things where it's like just annoying because you know you got to go refactor some code that was written a long time ago. Um, but you know, if the idea is like, hey, Sea of Nodes is cool because we can do all these graph rewrites to do optimizations and all that. I'm like, yeah, but I would just do bytecode rewrites to do optimizations, right? So, like, what's really the difference is the question. And um, I don't know. I don't know the answer to that, right? And so that's the thing is just this is what's hard. This is what's really hard actually about computers, and it's what invalidates like almost the entire academic regime of all these research papers and stuff, right? Which is someone proposes a new technique, and because it's their thing, they work hard on making that technique good and all this stuff, right? As you should. But then when they go compare it, they compare it to like a naive thing that doesn't have all that work put in. And it's like, well, wait, you should be comparing this. Like when somebody goes and decides what system to implement and they have choice A or choice B, you should be thinking of them putting an equivalent amount of work into either side, right? And so what do you get when you follow path a certain distance versus what do you get when you follow path B a certain distance, right? And that's just really hard to do because programming is hard and it takes a long time, and you know, human lives are short and all these things. And so you just never see that whenever anyone proposes any of these things. And but then when you go and decide what to adopt, that's the cost benefit analysis that you need to make, and it's just very hard. So I don't know. I don't have an answer to any of that. Um, Plowing through the memory over and over is the main bottleneck. Yeah, I agree with that. For us, you know, so far to the extent that we quote unquote optimize, which we don't a ton, um, it's about, you know, not emitting redundant things and stuff, right? Um, Although I just realized this morning when I was thinking about it that, you know, moving invariants out of loops is actually easy to do at emit time also. It's like we don't even need to switch to SSA to do that, which is kind of weird, shocking to think about, but it's true. Um, the only thing is just the annoying engineering thing of like if we want to move instructions out of a loop, we have nowhere to put them right now because our data structures don't have empty slots in them, right? Um, so I don't know, like a lot of these things, I'm just like, eh, like yes, you can do it that way, but you can also do it this way. And but on the other hand, right, I think we all know that, you know, when you go read a compiler book about how to make a compiler, like what they describe is way too complicated. A lot of these things are not that complicated. And so we should be trying to figure out what is what is the canonical form, what is the best way to make a modern compiler, right? And yeah, I mean, I feel like a lot of the things that I do in this compiler are probably more complex than necessary, but it's hard to tell what those are because we're also doing some things that other compilers don't do that are really complicated. Like I've said this before and it's probably accurate still. Um, about half of all the work that I've put into this compiler is simply into making the nonlinear compilation work, which nobody else does hardly. I'm not aware of other current languages that do it. So like, I don't know, man. Some features are just expensive and complicated and trying. All right, reading more of the comments from Mr. Smith here. The total audience for the hypothetical good talk is either 5 hours long or has an audience of 7-ish people worldwide. Fraction of people at BSC who have written compilers is probably about 30%. Yeah, I mean, I agree with that. I don't totally agree. I don't think it's 7 people worldwide. I think it's more people than that. And okay, so I wasn't at the conference, but I think that what you saw at the conference, what I certainly see from people who went there and are enthusiastic about it, is that they look around and they're like, oh, here's other people who want to do really good stuff, right? And so I think you have to think of the potential audience of such a talk. And again, I understand it's a very hard talk to put together. So I'm not saying go do this talk right now, right? But I think you have to think of the potential audience as being the 7 people you're thinking of, plus all of the motivated people who haven't had their enthusiasm killed by modern software yet, who are really, and like there, how do you get, when you get into programming, there's that fascination of like, oh, this is so cool the way this thing works, right? And somehow the way that people lose their enthusiasm for software is that mechanism gets engaged, and then it just kind of gets perverted into like, oh, it's so cool the way the object oriented hierarchy gets traversed in order to find a method 27 layers down or something, right? That's not actually cool, but like you can convince someone who doesn't know better maybe that that's a little bit cool, and then years go by of them dealing with this crap, and they get burned out, right? Um, anyway, the point being, I think the actual audience for the talk is a lot of people who would want to do compilers, except that they suck so bad, right? And so don't underestimate that. I mean, I think, yeah, that's the thing that I see from that conference is a lot of people are motivated. For me, when I go watch the talks, I haven't watched them all yet, not all the ones that have been released, but I've seen like 4 of them. And I feel motivated because I just watch the talks and it's like, wow, I thought programmers were all retarded now, and they're not. Like, there's actually some programmers who aren't stupid. That's amazing, right? Because you don't, when you look out on the internet, you don't mostly see that, especially if you tweet about programming like I do. Like, almost every reply that comes in is from, you know, mediocristan, um, and just people who want to maintain bad beliefs and all this stuff, right? And so I think that's motivating, and I think such a talk would have more of an impact than you might think, is what I would say. But like, dude, I know how hard it is to prep a good talk. Like, I just turned down a talk right now. Well, for many reasons, but one of them is I just don't want to do that right now. I got too much real work to do. Okay, so the key reason sea of nodes is good is because you rotate the boundary of the problem by 90 degrees. It's almost like the systems versus objects boundary distinction mentioned in Casey's talk. You could be wrong, but it seems like what you do when you do control flow graph rewrites, you end up with pass A, pass B, pass A, which has to operate on the whole CFG in each pass. Okay, here's what I would say is I don't know because we don't do control flow graph rewrites yet. But what I would say is I'm not sure. I'm not sure that control control flow graph rewrites really has to be a thing. And this gets down to, again, are compilers just crazy, complicated, and annoying or not, right? So, here, so people, maybe some people saw this talk at the Better Software Conference. One of the things that they talk about is building the control flow graph in a post pass of after sea of nodes. That surprised me a little bit because I thought that Cliff Click was an advocate for just generating the CFG when you emit the stuff initially and then modifying it incrementally if necessary. And that's what we do. I mean, we don't modify it incrementally, but when we emit, we just generate our basic blocks, and they're all known, right? Because only a small number of constructs generate branches within the code, right? There's if statements and loops, right? So which are a different form of if statement essentially, and like return, I guess, right? So I found it very easy. Well, I mean, very easy with the caveat that, yeah, we introduced some bugs and needed to do a little bit of checking and stuff, but it was very easy to just like emit basic blocks as we went. So the question is then, as we optimize, what does that look like? And I think that's one reason why I want to get to it soon, is maybe I can participate more in this discussion, because some of it is just like, look, I haven't done that much optimization of bytecode yet, so I don't know how it goes. But I mean, under what circumstances would we really want to rewrite the control flow graph? I'm not sure. Like, okay, if we move a bunch of stuff out of a block and the block becomes empty, maybe that's a case, but like, so the block's empty. Just delete it or let it be empty. I mean, who cares, right? Um, I'm just not sure. So I guess to think more thoroughly about that, I would need to be looking at a concrete case where it's like, oh yeah, I really want to rewrite the control flow graph in that case. I mean, maybe I guess getting rid of extra branches, right? There's like, do you branch to a branch, or I call them jumps here? Do you jump to a jump? Um, but that's not really. I don't think that requires CFG rewrites. I think you just change those instructions, right? I don't know. Okay. In sea of nodes, you can run all the passes on each node as you emit it, so you spend a lot of compute while the node is fresh and in L1. Okay, so the thing about that is that's also what I do, right? I just don't do that many of these kind of optimizations yet. But like when I emit a bytecode, so for example, you showed in the beginning the kind of pathological bytecode that you get from just like naively outputting based on a syntax tree, and that's accurate. That depiction was accurate, right? Um, but there's a lot of things you do to just cut down on that, and we do them, right? And so, like this bytecode that we're looking at here is a lot cleaner than what you showed in that thing. It just has this return value problem, right? Um, Now, that said, does that mean that if you printed out a large section of bytecode that I would be happy with everything in there? And the answer is no, because there's a substantial sector of these optimizations that we don't do, right? But if the statement is it's best to do the optimization on each node as you output it, I'm not sure that's any different from it's best to do each optimization on the bytecode instruction as you output it. Like to me, those sound equivalent. If there's a difference, I don't understand what the difference is. It might just be, that there's a structural engineering difference that like when you're in the mode of like searching on a graph, the code that you would write is just a little bit more general somehow. Maybe, I don't know. But like to me, it seems like the difference is like that, right? I don't, um, yeah, I don't know that it's more than that. Casey said it made him realize he should redo Handmade Hero. Yeah, I saw that. I think a short Handmade Hero would be really good. I mean, short would still probably be like 30 or 40 episodes at least, but I think that would be a thing that people would appreciate. Problem with the internet is people who get shit done don't comment. Yeah. Oh, totally. Right. Like the people who have time, especially if you're on Twitter, for example, and someone just says some really crappy, stupid comment at you, and you know that they're not a good programmer and don't know what they're talking about. Sometimes you go click on that person's feed and like that's what they do all day is send those comments. And then you're like, okay, okay, I know what I'm dealing with here. Anyway, so yeah, the upshot is I don't know. I don't know whether Sea of Nodes is the right way to go in the ultimate compiler or not. Um, but the reason I don't know is because it's hard to know. It's hard to know. I mean, I will say one thing that I don't love, like just the idea of doing graph rewrites. It just it just sounds like debugging that I would not enjoy, right? Now, of course, Raphael said in the Q&A, like, yeah, when we debug syntax tree stuff, sometimes it's like that too. It got a lot better because Raphael wrote just a pretty print function for the AST that helps a lot. Which I should have done a long time. It's not that hard to do, but it's one of those things where it's like, oh, I have to print every single node. That's going to be annoying to type in and maintain and all that. In reality, we should have done it a long time ago. Um, so you always have that you can do, but like, I get when it's just this miasma of nodes, it just seems really hard to deal with. Like we have an equivalent thing. So when we get circular dependencies in our compiler, one of the most popular bug reports right now is people generated circular dependencies, and the circular dependency reporter is not telling them in a communicative way what the problem is. And again, that's a thing where like we just generate a bunch of nodes for what is still waiting to compile, and we do like a graph analysis on that, right? We do cycle detection in there, which is not exactly something that would happen in Sea of Nodes probably, but it's it's just like a general graph algorithm, right? We do cycle detection in there, and then we print out the cycles, and it's just like I just hate that code. I hate it for various reasons. And maybe some of those reasons are not the same as it would be if we were doing a Sea of Nodes architecture, but it's just that's how I feel about algorithms that manipulate graphs is they're going to take a lot of CPU time. Um, you're going to have a lot of edge mistakes that are painful, right? But I don't know. We'll see. Twitter experts are fighting Ryan right now, denying that loading internet pages is slow. Dude, loading internet pages is so slow, it's unbelievable. Anyone who's going to argue that is like crazy. I should ban the word AI in this chat, but I'm worried that'll ban every word that has AI consecutively inside the word. It feels better to have a spinner showing than having the content immediately there. That is Stockholm Syndrome. Language is a lot simpler. You have a much lower complexity budget. Language has been designed to be one-shot compiled. Yeah, I mean, that's a huge difference right there. For one-shot languages, you're very convinced of treeless technique. Since you can do bubble up checking during recursive parsing, treeless has nothing to do with Sea of Nodes. Yeah, I mean, that's again, okay. There's like a more general problem here, right? Which is like, again, if you rephrase the current task as like, let's actually look at compilers as modern smart people who are not brainwashed by the decades of, you know, bad instruction about how compilers should be made. And you're trying to figure out what's the ideal compiler. Then, it's not like there's one answer. There's this dimension to the answer of like, how heavyweight is the language? How big is the feature set and all that? And so, harder to accomplish feature set implies more mechanisms in the compiler, which maybe implies that some other components of the compiler would make sense that wouldn't make sense for a different language, right? The problem with that is that's how everyone justifies all overburdened software complexity, right? Including the guys talking about why it's good that web pages are slow. Um, and so like the problem is that that is a justification for complexity, but you also don't want to be satisfied with that justification for complexity and say, okay, well, we shouldn't think about this anymore, right? So for example, I mean, so Raphael brought up in the Q&A that we use the AST, the abstract syntax tree. What is the word abstract doing there? Why is it not just syntax tree? I think it's because, again, in the 1960s, everybody thought this was a big deal. That's why lexical analysis is lexical analysis, right? Is because they really thought they were analyzing something originally because computers were so simple compared to today. Um, yeah. Anyway, I don't know. But yeah, I think if there's, for example, an open source example of like, here's a one pass compiler that does things in the simplest way possible, and whether that's tree of or sea of nodes or whatever, great. I think that would be a valuable example for people. Um, as soon as you say one pass, it's like, well, I can't do that, you know? Well, I think I can't do that. But again, I'm not sure. Like things are so complicated with this compiler, and there's all sorts of things that I'm trying to linearize more and make simpler and more direct that maybe we would get closer to, well, it'll never be one pass in the sense of like you call a function and it does all the things. But there's ways that I would like to make things simpler and more linear. Um yeah, I don't know. And so what does that mean for the architecture being different? I don't know. When it comes to the syntax tree, um yes, that is how we communicate to user programs, but if there were some other representation that we felt had equivalently good properties, then we could use that instead, right? The thing is, one of those properties is you have to see in the meta program a representation of all the things in the source program that you understand, and you want to be able to navigate between them, and that kind of implies syntax tree already. Like I don't know, right? Maybe it's because AST looks better than ST. I mean, maybe there is that. Like ST is a more awkward acronym, but I really do think a lot of these are just because people in the 60s thought all this was really complicated. You don't actually find it more complicated than doing an AST. You find it simpler only because previous iterations you would generate the AST and then walk it, the result being almost no gain. Yeah, I mean, yeah, and that's one of the things you were pointing at in the conversation that I had with Casey, right? Is like in terms of queuing up the things to compile, we want to compile things in dependency order. We do that just by uh generating the AST and walking it, and that seems really stupid. And yeah, I mean, if we weren't also using the AST for this other thing, then it would be like I would be much more inclined to be like, how do we get rid of that, right? Also, though, I mean, dude, I've been working on this compiler for a long time, and at some point, there's just like, look, I have a lot of problems that I want to make headway on, and whether we use an AST or not, maybe that ship has just sailed because it's so much work to change that I just wouldn't change it now. But then that's the function of other people making newer systems, right, is they can try these things as well. How is AST a tree when it typically contains type information which instantly turns it into a graph? It's all lies I tell. Well, the type information may or may not be on the AST. We do store it there. But I've thought about storing it elsewhere to little success. But the things that you're pointing at are outside the domain of the tree. So the type that you point at tends to be some structure that's of a different kind that's stored somewhere else. And so you're not ever pointing back into the same tree. I mean, come on, every integer is a pointer when you think about it. Anyway, I'm going to get a drink. Back in a sec. Some vitamins. We got to put some vitamins in some water. It's going to be real good. Does less passes help with multi-threading? I mean, maybe. What I would say is that what helps with multi-threading is having very few data dependencies between operations that you want to do. And the kind of web people who are retarded and tell you should do microservices all the time and whatever. Part of the reason they'll justify that is by saying, well, it keeps all the code simple so that there's no data dependencies so things can go in parallel or whatever, right? But in reality, like, data dependencies are what they are. You like can't really change them without radically changing the algorithm. You can't change them by refactoring some code, right? If you find that you could, then those dependencies were not real. They were things created by your bad implementation, right? But like when you write down an algorithm for solving a problem, the data dependencies are in the algorithm. They're not in the code, right? So, you know, and the problem we have in this compiler is just, dude, there's data dependencies all over the place. All over the place. And that makes it hard. Sometimes. In some parts of the compiler. In other parts of the compiler, there's not that many, and it's not that scary. They put it back in the glue. Well, yeah, exactly, right? Type strings, because every type gets parsed into a canonical type string. Yeah, that seemed weird. I wasn't sure why you would like that, but you even said at the time that people aren't sure why you like that, so it's fine. Whatever, man. When you have generics and stuff, type strings could get quite long. Also, I mean, we have multiple namespaces where you can bind things of the same name. So you couldn't like take the name of, well, and structs could be anonymous, but you couldn't like take the name of a struct as a type string for that reason because it wouldn't be unique. So you would have to append something to make it unique. At which point, if the strings have a lot of trash in them, what's the point of them being strings? I don't know. Is it possible to get a procedure name from type info procedure? No. Not currently. And the reason is because our particular procedure type is not bound to any name. Like why? Okay. In a language like this, Why do procedures have types? It's so that, well, two reasons. One, when you call the procedure, so I guess that's what you're thinking about. But the other one is like, look, if you assign a function pointer to a value of something else, are they the same type? Is that a valid thing to do? And so if you think about a function pointer that's of a procedure type, what's the name on that type? There isn't one because the type is compatible across a lot of things, right? And so there is no such name stored there. If we were to store a name, it would just be the name of the first procedure of that type, because we don't generate a new like if you have a procedure that takes no arguments and returns nothing, you might have 100 of those in your program. We're not going to make 100 types for that, right? You don't want 100 types for that. You want one type for that. So it just, the concept of having a name there doesn't make sense. Although I will say this is a somewhat commonly asked question that people have. Is the place to get the name of the procedure is from the syntax tree node for the procedure, not from the type of the procedure. Is there any way to find all procedures that match that type info? I mean, you can do that from a meta program because you see all the procedures go by. And you can just pluck out the ones that are of that type. If you mean from the runtime program, there's not really a way to do that. It would be possible in principle, like if we made a segment full of that data, right? But that's also now something you could do yourself. Like, again, it would require metaprogramming, but you have a metaprogram, snoop all the procedures, and then you build a table of them and you put that in a data segment. And you can put procedure type. I mean, you would have to serialize that, so it's a little bit annoying, but you would put the names in there. I don't know. How is Sokoban doing? It's doing good. It's doing good. I need to take a few days off because I've been working hard on it, but yeah, we have playtesters playing through the game, and they're pretty far at this point, and they're enjoying the game as far as I can tell. So that's great. Do I plan on making a generic optimizing backend library? That's not in my plans right now. I mean, I always believe in solving the specific problem that you have if you're trying to generate the highest quality solution. And then if your high quality solution has benefit to other people, then you could think about factoring that out. So that's the way I would approach it. And such a time would be so far in the future, I wouldn't even, yeah, we have a lot of work just to do on this compiler, man, you know? But when we release source, people can do with it whatever they want. And if they wanted to make such a thing, they could do that. But like I'm saying, like I said at the beginning of this talk or VOD, which you might have missed, part of the philosophy of this compiler is to emit bytecode that's not that bad and not lean on the back end optimizer so much. So, I mean, that doesn't necessarily mean that the eventual backend optimizer won't do all the optimizations, but it does disincentivize that a little bit because it means that to get to a certain level of performance, the backend would have to do a little bit less relative to some other compiler with a messy front end, right? Do I do play testing the generic way, or do I think I have a different approach from, let's say, AA studios? I don't know what AA studios are. I also don't know what the generic way of playtesting is. So I don't know how to answer that question. What's wrong with having the back end doing the work? Because as I explained, you can go back and watch the VOD, but like it takes, it obviously takes a lot of time and CPU heat for the backend optimizer to search out and remove all these extra instructions. That's a search problem. But guess what? Not only does that take time, it took you time to emit all the extra instructions in the first place. So you spend a bunch of time doing extra stuff, and then you spend even more time getting rid of that extra stuff. Now, this is not the only reason why modern compilers are so slow, but it is one of them for sure. How many common backend optimizations are targeted at program made by people who do weird stuff, like writing 10-line functions, which all have to be inline? Yeah, I mean, that is part of it. So, you know, if you look at LLVM, it was designed in large part to optimize, you know, code from Clang. And that's like all this template heavy, tons of layers of indirection and abstraction on things and whatever. And it's like, you know, maybe just don't write that code and you wouldn't have such a big problem. Okay. The new C++ standard print hello world took 2 seconds to compile. I am Jack's complete lack of surprise. Dude, it's such a travesty what people are doing with computers. Okay. I actually just noticed actually in this example, this is a redundant move with this, right? And I think that's just when we're dereferencing structs, we don't we don't try to match that. And so the question is, how is the best way to do that? So when we emit constants, for example, the way we prevent emitting duplicate constants is we just literally say, look through the constants that we already emitted, right? And same thing with lees. We say like, what addresses did we already emit? Um, for something more like this, maybe it's just like, this is a dereference. Just look for dereferences if you know there hasn't been aliasing. I mean, I guess that's the thing is like we don't know unless we do analysis that nobody wrote. Like, yes, this is the same move, but maybe in here somebody wrote to that address and we don't check that right now. How do I get into very deep think mode? I mean, I just don't stream on the internet and go off and think about things. Okay. So, yeah, I mean, in this case, you can, of course, like, since there are no rights between these two things, it's very obvious that this can't have been messed up. So you could just use V9 here. However, if you implement that optimization, you have that question like, how often does that really apply? And it wouldn't solve the problem as soon as there's any right to anything in the middle, right? So, so maybe you need bigger guns for that. Do some data flow analysis or whatever. I don't know, man. I mean, since this is on the stack, like, I mean, again, you could be like, I happen to know that I didn't take a pointer to the stack anywhere in this function. If you do, all bets are off if that pointer is written to, like, yeah, I don't know. That's a whole thing. It's a whole thing. Okay. Let's try to make some progress on this refactor while the stream is still going. Do I ever collect heuristics on how often an optimization would be applied? Yeah, I do sometimes. We might actually do that. One stream that I thought of doing this morning instead of this was SSA impact report. So this is not single static assignment code, which you could probably see somewhere. Maybe not. Like, here's the thing is if you naively output bytecode, it's largely SSA anyway. Oh, I mean, we do some assignments down here, I guess. They're a little bit hidden. Where was it? Oh, it's in our other code. This one. So this is our thing where we just call a lot of functions. So here we're actually doing this call and then we're assigning to v5. This is one of the trash instructions. So because we assigned to v5 twice, this is not SSA, right? But almost all of our assignments are SSA equivalent. And so, you have some occasions like this when you reassign a variable and you have, okay, like anytime you do a loop, for example, that needs to be changed if you want to do SSA. So the question is, how bad would it be to go to SSA? The reason I didn't originally was just because, like, well, I'm not sure how much more expensive it's going to be. I'm not sure if it's necessary. I'm still not sure if it's necessary, but it would make some things simpler. So the question is just, how much does it cost? So I was thinking of doing a stream sometime where we just say, well, it would be this many extra registers, this many extra move instructions, and whatever. Okay. So when we last were actually looking at the code, um, we wanted to get rid of this return register base. And so, yeah, um, I actually wonder. I actually wonder if we can just get rid of this here. Um, just one by one. So like I said, we have this proc info um, with the local register in it for the, maybe we set that here. Let's see. Okay, so here we're trying to do register placement. We even had this marked Weissman score. Dude, so I did all this work at some point. Okay. But I turned it off because it was causing problems or it just wasn't done, or I don't even remember. This was a long time ago. Um, and this is just for large return values anyway. Um, oh, guys, we're literally just, remember how I said we would make this array with return register base plus I? That is literally what this is. This has been done. Have I ever looked into GCC's nested function extension? Wonder why they decided to just make stack executable instead of moving the code. That sounds terrible. What? Are you sure about that? The code is on the stack? That, dude, GCC has got to be. I mean, certainly when I look at the user level code, like the libc for GCC, it's horrible. Like, I wouldn't trust those people to program anything. So, like, I'm not surprised by what you're saying. Oh my God. I mean, maybe that was done in like the 1970s and it made some sense to somebody at the time. If that was done anytime in the 90s or after, that person is just fired. GCC is fast executables though. No, it's not. Not compared to like Visual C++. Okay. So instead of using return register base in some of these other places, again, we can be very careful and do this step by step. So one thing we can do, instead of just swapping what we're using when we say return register base plus whatever, in the bytecode runner, we could just say assert I actually don't understand. So I was about to say assert that these two things are the same. Wait. Is it local register that gets set? Result register. ri.local register is result register. So like, I guess these, oh, oh geez. Okay. So the deal here is we're doing a compile time execution thing where all right, we just lost a peripheral again, whatever that was. Great. Mouse still works. Camera still works. Maybe. Hello? Yeah. So when we return, we are copying everything from the callees stack to the caller stack, right? Essentially. Now, part of the reason that this system was designed the way it is in terms of calling convention and stuff is so that we don't have to do this. Um, and so the question is, where is best to store the thing? So I'm actually wondering if this is just really old code because like when we compile stuff, right, to our normal backends, they can't do this copy, right? Because when you return from the function, um, the stack is gone, right? So maybe we just need to make the bytecode runner work more like everything else. Uh, okay, so this is emitting code for a procedure call x64 backend. Um, for all the returns, I don't, dude. Ryan's register allocation code that he wrote is full of like FFs, and I hate it. I hate it. Um, okay. So C call is a giant mess, right? If we're not a C call, if it's a big value, we put on the stack or we generate. What is C? All right, that's just the buffer. What the hell is temp? I don't know what that is. I guess temp is the register. So this is reading the value number. And this RSP, this is just how we this is weird. Like, we shouldn't necessarily be doing this because maybe this is in a register. So like some of this code should be a little different than it is. But even if this happens to be in a register, we are reading it off the stack. We pass that as an argument. Okay. So it looks to me like all right. Dude, there's so much C call crap in here. How we pass the context. So much C call. All right. So this is I think we still haven't done the actual call yet. Compilers. So we're loading something off the stack into A as a temporary register, and then storing A into that local register where we expect things to be. Okay. This is using that register base. So when I said that we don't necessarily use this in machine code generation, that's not necessarily true. This is the return register base. So we are using this even in the back end here. For small values, at least. Let me see. Do we use it down here? Yes. Big values got filled via memcopy and poke return. Okay. Poke return value used to be an explicit bytecode instruction. We don't do that anymore. So this comment really means earlier up the loop. Okay, I don't love this. I had wanted to do a stream where we would go and start eliding these instructions right away, but I need to go back and do a bunch of other stuff first. And maybe I'll just do it off stream. And then we can do a fun stream that's actual progress, because this is not really actual progress. I guess the question that I have, it could be addressed one thing at a time. So here, it's like, okay, we're pulling this off the stack. That's fine for now. We don't have a calling convention that returns things in registers anyway. But um, yeah. Yeah, I don't like how there's so much register allocation pollution code in here. It makes me sad. But I'm not sure, I'm not sure what the cleanest version of that is either. Okay. So the big values happen up here, and we can attack these one thing at a time. The reason this is annoying is, like, if we're going to change something here, which I'm still not sure if we need to, but if we do, so basically what's going on is, in the bytecode runner, we're copying it to the return register base plus whatever in the calling site. But here we're setting this stuff like value number or storage for big return value, right? This is a linear allocation struct. This could be on the stack or on, in global space or anything, right? And so if you had an assignment to this argument, in principle, we could set this, and we probably do set this, to an existing variable, right? So, like, I just need to look at this code for a while and get it into my brain again, is basically what has to happen. And then we can do a stream where I clean it up and stuff, or the step one is to get bytecode runner to stop using return register base. And that may be just a matter of making that code do the equivalent of this. But maybe not, because like I said, this thing uses this base variable. Not that, not that. this thing. Where are we? This is after we return. So basically, the idea behind this calling convention is that we would just pass to this function um, the addresses of all the things that it needs to write out when it returns, right? And those addresses could be addresses of things that already exist, or maybe not. Now, the problem that you always have, I guess it's never going to be really slower in this case, but sometimes you're like, well, it takes space to say all these addresses, and then the function has to load them and whatever, right? But if you return and you have to copy them anyway, then that's at least better. Yeah, so the next step for me is just going to be to just stare at this code for a while today and just make sure, because I could go start changing it now, but it would still be like, I don't have a super clear picture of what's the right thing to do. And sometimes that's a fine way to program because you're just like experimenting and whatever. I don't think that would make a very good stream because it would just be me doing stuff and being a little confused and backtracking and whatever. So I think what I'm going to do is just look at the code and make sure that this is what I want to do. Like the plan is, I think, to just pass pointers to the return addresses as extra arguments, right? Um, that was the plan all along, I think. And I just did this as a temporary thing. And I forgot that we never did that. Right. And now the thing is it's kind of a big change. It's kind of a big change. There are several, I'll at least describe what you got to do, right? So right now, functions, when you call them, are reserving space for all their return values on their local stack. And then we're copying them off. And you don't want to do that, right? Instead, you pass one extra argument per return value, and it's a pointer to the return value. And you need to allocate space for those at calling time instead, right? And then the callee, when it goes to return a value, needs to, essentially read those and use them. And that's just, it's a lot of changes to do at the same time to two backends and compile time execution. Like this could be like a multi-day thing just to change this. Which doesn't mean we shouldn't do it. I mean, we absolutely should do it because, like I said, this has been the plan all along to have this work this way, right? So you should, and the reason is, if you have some function that returns a vector, and that's called by some other function that returns a vector, and that's called by some other function that returns a vector, you should be able to use the same storage for the vector through all three of those call sites, right? And you just pass the pointer through every time. That's what you just want to happen, right? And right now, that is not happening. Now, that said, okay, what I just described makes sense. What I'm not sure then is that other code where I already sort of wrote this. What was that doing? It was like trying to use value placements, but yeah, okay. I think there's actually two parts to this problem, guys. I think this problem, okay. I think the conclusion I'm coming to is these copies are even worse than it looks. Okay, so here, remember this was our little function call example. And in these cases, when it's big values, we're doing call and then a copy, or sorry, that's a value copy, but let's go to just this one. So we do a call, we return to v3, we get the address of v4 and we memcopy into v4. What I'm realizing right now is that there's even an extra copy that we're not even talking about. Okay. That's part of why I'm confused and looking at this code and it's taking a long time. There's even more copies. So the whole thing I just said about the calling convention and passing the pointer for the argument and all that, that gets rid of the copy that's implicit in here. We don't write that copy like this because it would be a lot of instructions for pointless. But when we return v3 on stack size 16, that is a copy from the stack of the callee. And then we copy it again. So there's literally there's two copy operations. There's three copies of the data here. There's the copy in return struct that gets allocated on its stack locally. There's the copy into our stack, and then there's the copy into the destination variable where we want it. So that means there's even more work to do than I thought. And that's why, so I was confusing these two things back and forth. These are different copies. So I think first we want to get rid of this copy that's the bytecode instruction copy. And that'll cut down the number of instructions. We'll still have this implicit copy here. And then we can do a separate stream where we get rid of that. And that's a bummer because we have to do more work than we thought we did. But the upside is we improve the generated code much more, right? The reason this copy is hidden is there's just not a good reason to have a ton of instructions. Like the backends just know how to do this, right? So, yeah. Why is my stream for certain audiences? I don't know. I don't think I set that. All right. Let's see if any on topic questions came in. No, 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 no. Dude, don't read chat. Don't read chat. Oh my God. Elysian Fields of Ancient Greece. Yes. We would like to visit the Elysian Fields of Ancient Greece. We're not quite there yet. Okay, this is good news though. So I'm going to take a break and go have my day. But the good news is, well, and I'm also just going to look at the code a little more off stream to just make sure I really get it. Um, but the good news is I think we can go and do the instruction copies without doing these copies yet. And we can attack these copies separately, and that's good. And we can even ship a beta of the compiler that has these out. Yeah. I'm just a little bit confused about the return register base thing. I'm a little confused about that. And how that might still be a little different in compile time execution versus other things. Right. So here, I mean, we're copying small values, I guess, but we're getting the size. I mean, this is literally the same code spammed twice for small values for allocated registers. Like I don't like it. I don't like this. Um okay. This really shouldn't be doing this. Honestly. We should be able to remove that check later. Um yeah. So this local register value, what I'm confused by is the following. Here's the return register base thing. This is in space that was initialized by the callee. We put a bunch of stuff in there in the callee, and then we return out, and then we're moving it to here. And but these, I seem to remember, were being set to return register base plus whatever, which doesn't make sense to my brain right this second. Now it could be that it's my return register base. Maybe this is a different. Okay, hold on. We're not even looking at the right thing. This thing. Maybe this is a different return register base, and I'm just using the same name for a similar but slightly different concept. That happens sometimes. let's see. What do we pass there? Thank goodness there's only one caller. Result value number base. Okay, okay. Okay, that's starting to smell like a local. Result value number base. Okay, yes, we just allocate this right here. Okay. So instead of doing this, we could put that in those somewhere. We can just, I mean, so right now, again, instead of this being a base and a count, this should be an array of an array of value numbers of where to put the results. And then once we have that, those value numbers can be whatever. Okay. So there's just enough moving parts flying around that I get them confused with each other. And part of that is like, okay, man, well, just have fewer moving parts or whatever. So this emitting call, I hate this peak thing. Stop it. Right. So this is where we can just, in fact, we have one for arguments for macros in here. So on here, we can just generate these and then store that array here. And if some of those need to come from elsewhere, as we want them to elide these copies, then we would just put those value numbers in here. And then if we don't have a copy elision to do, then we just do this same new value we're already doing and put that in the array. Or if we don't actually receive the return value, maybe we just put something in there that says dump it. Although I think that would only be helpful in the short term, because when we change the calling convention later for that other copy, we don't want to be like checking for null because they don't want the argument. It's just like, look, you have to give me a place to put the argument. That's complicated too, because I guess for small values, there's no reason to pass a pointer like that. Like that. I need to think about that. The calling convention should be as simple as possible, but like it's more instructions to push these pointers probably if you have a bunch of small return values. I don't know. All right, everyone. I'm going to go have my day and look at this some more. Let's find someone to raid because I'm sure. Let's just. I used to be able to do this and just get to the software and game development channel. Sad. Now we have to figure this out. How do we get to software and game development? There we go. Someone was playing a shooter. Radix tree. Why are we getting someone's music? Why can't I scroll? What is how do they keep ruining Twitch? Like what is going on here? Why did they decide that half my screen should be one stream and then I can't even scroll this off. This is just they have decided that this is the featured streamer who I must see. And I just can't. You have to click more and you can remove it. Oh. Like what? It's like they're taking okay, no, cuz still I can't. The button in the top right above the screen. What is wrong with these people? Literally, what is their major malfunction? Let's see what Dungeon Man's is up to. Diffing. C sharp. Move damage code to con. Okay, we could do Dungeon Man's. Um, I don't know, dude. I'm looking, I don't see anything. Making an adventure puzzle game.
Line quality changes. Don't like that.
I mean, that looks kind of cool. Doesn't look like programming is happening, so. He's watching Twin Peaks. That's a great way to not be distracted while you're trying to program C++ is to watch Twin Peaks. I don't know, guys. Okay, we're gonna raid Dungeon Man's, and that's all there is to it. But we still got our game.
It's lo-fi na Spotify. Jako play
What is going on? Gothic remake. Okay. Okay, we we'll just do this. Look how fast that web page loaded. It was only 2 seconds. All right, thanks everybody. Maybe we'll stream tonight after I look at the code some more, and we'll try to finally solve this thing.